Hello mathematicians, we're now going to have a look at the applications of differentiation of the log function. What we need to remember is, as I said at the end of the last video, that the result of differentiation has exactly the same significance in terms of the slope of the tangent and normal, and locating and determining the nature of stationary points, and therefore for sketching curves, as we've already covered in the course. They're just a few extra little additions, and there are two limits worth considering, and that they are these ones. So the limit as x tends to infinity of log of x divided by x tends towards 0, and the limit as x tends towards 0 of x multiplied by log of x is 0. And the reason for this can be deduced by looking at the curve. So if we look here, we've got the curve of y equals x. We've got in green here the curve of y equals log of x. Now, when we look at the product of those, x multiplied by log of x, then what we see is that we get this blue curve just here. So that when x equals 1, of course we've got 1 by log of 1, which will be 0. But then as we go beyond 1, we can see that we continue up. Both y equals x and y equals log x shoot off towards infinity, but y equals x goes faster. So that's the product of those, goes to infinity even faster. At this point here, they cross each other, and at 0, y equals x is the dominant as opposed to the negative infinity for y equals log x. So x is the dominant function rather than log x for their product. And a similar thing happens when we travel off to infinity. So as you travel off to infinity, log of x, as you can see, is going to head towards infinity. Y of equals x is going to head towards infinity, but again, y equals x is going to head towards infinity faster. So as we go out, we are dividing a big number by another big number, but one which is, in a sense, getting bigger more rapidly. So the result is that the quotient of the two tends towards 0. So in short, what we can say is that x is going to dominate log e of x when they turn up in the same equation. So let's have a look at some examples. First one, write down the equation of the tangent to y equals x. So familiar language, at a particular point, hence find any values for which the tangent passes through the origin. So let's just do the first part, write down the equation of the tangent. We know the process for finding the equation of the tangent is going to involve us differentiating our expression to begin with, so that's just 2 on x, no problem. At that point, we're basically finished the new stuff. So from here on, we want the gradient of the curve at x equals c, so that becomes 2 on c. That's the gradient of the tangent. To find the equation of the tangent, we plug it into y minus y1 equals m outside of x minus x1. y1, of course, is just what we get when we put our x value into our equation. And so there's probably not much to be gained by rearranging the equation from here. This is the equation of the tangent. And then we want to find any values of c for which the tangent passes through the origin. So again, think about what that actually means. And it is that if the tangent passes through the origin, then 0, 0 has to satisfy the equation of the tangent. So when we put that x and y value into our tangent equation, we conclude that 2 log c equals 2. Now we have to solve that equation to find c, and the way we do that, first of all, is to shuffle any constants so that all we've got on one side is log of something. So divide both sides by 2, and we'll get log c equals 1. And when we have it in the form log c equals 1, we use the fact that log and exponential are inverse operations, so we undo the log by taking the exponential of both sides. And we're taking the exponential, remember, to base e. So e raised to the log c gives us c, and e raised to the 1 just gives us e. So this is the value of c for which the tangent passes through the origin. Now for our next question, find and classify the lone stationary point of y equals x squared log x in its natural domain. So we know what a stationary point is. We know what a domain is, hopefully, as well. But for a stationary point, we know the process is to first of all find the first differential. So we can do that. We've got a product. Put down the first, multiply it by the differential of the second, which is 1 on x, plus put down the second, multiply it by the differential of the first, and then tidy it up. And we want the stationary point, so that happens when y dashed equals 0, which means that x outside of 1 plus 2 log x equals 0, but we can't have x equals 0 as that's not in the domain of log. We can't take the log of 0. So therefore this bracket must equal 0, which means 2 log x equals minus 1, and same as before. Shuffle it so that we get to that. Take the exponential of both sides, and we see that we get to e equals minus a half. Sorry, x equals e to the minus a half. What does that mean? It's just a number. It's 1 on the square root of about 3. So it's a positive number, and it's a number a little bit bigger than, no, a little bit smaller than 1. Okay, next part, show there is an inflection. Well, again, we know what an inflection is, and it's just an inflection, not a turning point, which is also an inflection. So an inflection occurs when the second differential is 0, so we find our second differential, and we find when that equals 0. So when x equals sorry, I'm a step ahead of myself here. We find the second differential. We're still at the point of classifying the stationary point. So when we find our second differential, we plug in the point we're after. We notice that that's greater than 0, so what we have is a minimum turning point. Now, the next part, show that there is an inflection at x equals e to the minus 3 on 2. We take that second differential, set it equal to 0, we go through and we solve that, and we get x equals minus 3 on 2, as expected. And again, what is that? Well, that's just a number. It's a positive number, and it's the square root of 2.7 and cubed. And after that, examine the behaviour of y and y dash as x tends towards 0 from the positive side. Well, as x tends towards 0 from the positive side, this product of the two tends towards 0, so the x dominates. X will tend towards 0. And for the first differential, it's x times 1 plus 2 log x, and again, x will dominate, so it will tend towards 0. So as we head towards 0, the value will tend towards 0, and the slope will tend towards 0. And of course, we don't actually reach 0, so when we draw our graph with all of this taken into account, we have an open circle at 0, because it's not in the domain. We cut the axis at 1, because if we look at our original expression up here, when x equals 1, we've got 1 times log 1, and log 1 is 0. So we cut through there at 0. We've got our minimum turning point here, and we've got a point of inflection just here, where you can't tell it from my diagram, but it is concave up, and then it's going to go concave down as its slope is heading towards 0. It's flattening out as we go towards that curve. So have a go at these out of 12C, and remember, apart from actually differentiating log and maybe what happens with limits, there is nothing new here.